Okay, can everybody hear me? Okay, great. So welcome to the last talk of the track today. I'm going to give you an introduction to Portable Native Client, or something we call PNaCl. My name is David Sehr. I'm the tech lead of the NativeClient team, and let's get started. So, since I'm going to assume that some of you probably haven't heard about NativeClient, I'm going to give you a little background to start with. I'm going to talk to you about NativeClient, about why having C++ code, running it in the web, is a good idea, and I'm going to talk to you about NativeClient and how it makes it something we can really do. So, I don't think I need to tell most of you, but there's a lot of good C++ code in the world. Maybe a little bad C++ code too, but a lot of good C++ code out in the world. People have written a lot of great applications, things that take advantage of sort of the natural advantages of native code. Things like performance, low-level access to operating system features, etc., to create a really rich and immersive experience. These sorts of applications would be great if we could bring them to the web. But the problem is, you really can't bring them to the web as they are because it's not really safe, right? You bring native code to the web and you open up all the possibilities that we've all come to know and hate about the web, which is insecurity and all the things that can come from that, like having your identity stolen or whatever. So what you'd really like to have, you'd love to be able to bring native code to the web, but you want a secure execution environment that can contain the bad stuff, make sure that it can't do bad things to you, while letting the good stuff run, which is what we built with NativeClient. Now, NativeClient's been a feature of Chrome since Chrome version 14, about a year and a half ago. We built this for x86, had a big launch party you might have seen, and it's been a persistent feature of Chrome since that time. About that time, same time last year, as the Samsung Chromebooks launched, that Sundar talked about in his keynote, we brought NativeClient to ARM. And since that time, we've been bringing native code to the web with performance 90-ish% on x86-32 and 80-ish% of native code performance on x86-64 and ARM. So you can build the cool applications that you've always built in native code, but bring them to the web. So when we started doing NativeClient, we built a few applications. We ported a few things and said, we'd really like to showcase what are the cool things that people can do with NativeClient. And we continue to do this. I've got a group of people that work with me that are continually porting a few applications and saying, here's something that shows off a new possibility, say vector instructions or some other feature that we'd like to show off. And we think there's some amazing potential shown here. And we're not alone. Over the last year and a half or so, over 30 applications, 30 games have been ported to NativeClient. And you can go to the Chrome Web Store and you can download a bunch of the titles that I've shown here, plus a bunch more. So 30 plus games. And more recently, applications that are probably not in that category. Things like productivity applications, applications to do secure shell accesses, or remote desktop viewers for NativeClient. So there are lots of other things outside of games that we're also bringing. Things, for instance, with Chrome RDP and with SSH, it's the cryptography performance that we can bring with native code opens up a new class of applications as well. So lots of applications have come. We think the potential has been seen by a lot of people. And also, people out there have been doing these great applications and seeing the performance that we provide. So you probably are asking yourself, if you haven't done this before, how do I build a NativeClient application? Well, it's a native compilation, basically, as you've always done. You take your C++ source code, in this case, use a custom compiler. I have a compiler based off the GCC toolchain, and you build something called a Naci. And that's a native ELF binary, and it's portable across operating systems. It runs on Windows, Linux, Mac, ChromeOS, but it's restricted to a particular instruction set architecture, to x86, 32, or 64, or ARM. So actually, if you want to bring the full experience to the full range of Chrome platforms, you'll use a set of custom compilers, you'll build a set of Nacis, and that will be the starting point. You'll add something that we call a manifest file or NMF file, and then along with that, you'll build a web page, and the web page will use an embed tag. And this embed tag tells where to find the manifest file, and basically that this is going to be a native client-enabled application. And with that, you have a native client-enabled application. So this is what the developer needs to do to build an application. What does the user see when he surfs to a page that's native client-enabled? Well, first of all, we need to talk about the manifest file. We talked about the manifest file before, and the manifest file serves several purposes. But the major purpose of the manifest file is to tell the browser where to find resources. So where to find resources can be a lot more than just this in the case of dynamic linking and some other things, but you at least need to say where to find the native client executables. And you need to have an entry in this manifest file for every one of those executables that you provide. So that's basically for one target the native client version of your application is going to run on, you'll need one entry in this manifest JSON dictionary. And that's going to tell for which ISA where to find the native client executable. So back to the user. When the user points the browser at a native client-enabled web page, the browser sees that embed tag and says, native client, I'll need to do something with that. It'll load the manifest and say, I'm running on an x86 64, so I need to find my resource in this particular location. Once it's found that Naci, then it loads the Naci and puts it in something we call the native client process. The native client process is a key part of the whole security story that we've built with the native client system. The native client system is built around a technique called software fault isolation. The software fault isolation is a scheme for basically analyzing and ensuring that the Naci doesn't contain any forbidden instructions. Typically, those are the ones that allow direct native access to the operating system. And that furthermore, it behaves itself with regard to control flow. That is, it can't run any instructions that I didn't look at. And data flow, that it can't touch other memory in the browser or even in the native client process that I'm looking at here. So it can't look at your cookies or look at your SSL keys or things like that. It can only look at the memory that the software fault isolation sandbox allows it to talk to. So once the validator has scanned the Naci and has confirmed those properties hold, then execution of that executable can start. So once the execution of the Naci starts, again, you still cannot have raw, unfiltered access to the operating system, because that's where the root of these security discussions we talked about before is. So anytime the native client executable needs to do an operating system service, say to load an URL, or to talk on a socket, or read a file, it's going to talk to something we call the native client runtime. I like to use shorter phrases than native client, so I'll say NaCl quite a bit here. You'll hear me say that several times. So the NaCl runtime actually is what the executable interfaces with, and the NaCl runtime is responsible for checking that the executable has the privilege to do the things that it's requesting to do. And if not, it can always abort the execution. So with this in place, so the executable has been scanned, the native client runtime is monitoring to make sure that only secure accesses are made. You've got a process that's running and it's safe, and you've got a browser, but they're not talking to each other. So how do we make them talk to each other? Native client executables are going to be plugins. So the web page that we talked about before created an embed tag, which is the classic way of loading a plugin. In this case, this is an out-of-process plugin. It's something that's going to run in the secure environment we created, and it's going to talk to the browser via something we call PPAPI, or Pepper. And PPAPI is a rich interface, having 2D and 3D and audio and video and other things like that. But the simplest of interfaces is you just start a plugin, and you can post message back and forth between your plugin and your page. And with that, the plugin becomes an extension of the browser's capabilities. So I think you can see the potential. Now we brought native code, we've made it run securely, We run it in this environment, and we can interface with the web browser to do cool things. So there are a couple of limitations yet. We didn't want to bring native instruction set architectures as part of the web platform. Why not? Well, anytime you list off the set of instruction set architectures there's always one more that you didn't list. And what do you do for that? Well, there won't be an entry in everybody's manifest, there won't be support for that, and this will cause lots of user confusion. And there are also security reasons about this. The very low-level accesses to instructions cause issues that I'd be glad to talk with other people about offline if you actually allow them in the open web. So we didn't want ISAs in the open web platform. But we really do see there's tremendous potential to this, right? There's great performance. There's the ability to create these applications in the web, and we wanted people to get at them. So we made native client executables available through the Chrome Web Store. And so you can go to the Chrome Web Store, and it just so happens that at the top of that, Pages Don't Starve, which just so happens to be a native client-based application. But you can see any of the 30 games that I talked about before are in the Chrome Web Store. Or if you're wanting to develop yourself, there's a flag that you can toggle that'll allow you to run things yourself. But by default, we have limited native client execution to running out of the web store. So we're done, right? We brought C++, native applications, we run them in Chrome, and they're deployed in the web. What else could there be? Well, we said we really didn't want native ISAs in the web. So what we'd really like to have is something that wasn't a native ISA, that you could package up on your website, download, and have it become something in the native ISA so that it can run on your platform. So that's what brings us to Portable Native Client. So Portable Native Client, so we talked a little bit about this in the Native Client introduction. It impinges on the cycle all the way from the developer to the user. So the developer and the distribution and the user, I'll talk about those, starting with the developer. So you as a developer you probably already have a C++ application. Maybe it runs on a typical 32-bit machine. A typical 32-bit machine might be Little Indian, might be Big Indian, but I think for the most part, things are Little Indian nowadays. And you want to make it so that it runs on all those platforms you had before, that is Windows, Linux, Macintosh, ChromeOS, but you want it to run across all the instruction set architectures as well. So you've got this cool application. Say in this case, it's this secure shell thing we were talking about before, just chosen as an example. And this is also kind of interesting because in the secure shell case, as opposed to a game which typically will put up a 2D screen and manipulate it all directly in NaCl, the UI in my secure shell application is done in JavaScript. So it's an example of I'm doing the cryptography in the native client executable in the UI in JavaScript. So it's a really a different sort of model and one that's doing a lot of post messaging back and forth. So you'd like to bring that to the web. So the development cycle looks a lot the same as it did for native client. The development cycle starts with you take your code, use a custom compiler. In this case, it's PNaCl Clang or PNaCl Clang++ to compile the application to an executable. Now this case, so PNaCl Clang is based, as you might guess from the name Clang, for those of you who are familiar with LLVM, it's based on the LLVM set of tools, okay? So the executable that's produced is no longer an ISA executable. It's an LLVM bit code, or what we call PNaCl bit code, with some simplifications and with some versioning for making it backward compatible across a longer set of lifetimes, but it's essentially LLVM bit code. You again pair that up with a manifest and an embed tag and build your web page as you did before. And you get the cool experience that the user wants. So this was the developer side. What's the user going to see? Well, back to the manifest again. Instead of, previously you remember we had one line for each of the ISAs that were supported by the application. Instead of that, we just have one. And the one says it's portable. We still have to say where to find it. That's an URL. And there's one other little gadget I'll tell you about here a little later. But the developer, when he put that up, can say where to find the performance setting. So basically, this will be a trade-off between translation time and full bore performance. So the user, when he starts things up, the browser sees, again, the embed tag. It looks at the manifest file, and it sees there's a portable executable. And this time, instead of immediately starting the native client process, it has to start something called the translator. Now, the translator has the responsibility of taking it from this portable executable format and producing the ISA-specific executable that runs on the platform. I'm still on an x86-64, so it produces a Naci. Once it's produced that Naci, it again passes that to the native client process that it creates, because we've already shown that we know how to run native code securely. So once it's translated, it runs the same way as it always has in NaCl. So what's more, the translator is more than just a compiler backend. It's more than just the part that takes the bit code and produces native code. The translator is responsible for taking basically the PNaCl, and the first thing it does is see, do I already have a translation for that? And we have a translation cache, and the translation cache will keep track of all the times that we've previously translated it. If there is something there, voila, we start the native client process, and off we go. If not, we have to start the translator. And again, for those of you who are familiar with LLVM, this will be familiar. LLC is the back end of the LLVM compiler toolchain. We'll start LLC. And LLC will stream the executable down from the web. So we've changed it to interface with the web to actually pull the PNaCl down. And while the PNaCl is being pulled down, it will be translating the previous parts that have been pulled down. So we dovetail translation with download, and it'll produce a Naci. And you might have noticed it's running on a native client process. This is to provide additional security from attacks where somebody puts on a malicious page a PNaCl that tries to own the translator. In previous situations, there have been language environments that had JITs that were exploited by unscrupulous pages to do things. And this is an additional level of secure execution for PNaCl. So once we have the Naci, we put it in the cache and off we go. So you're probably asking yourself, this guy's up here talking about all this compiler stuff. I think it's really cool. We've got compilers, we've got caches, we've got native client executables, and I'd love to talk to you about that. But you're asking yourself, how do I use it? Well, I have some good news for those of you chomping at the bit to get using it. We have a developer preview in Chrome. The developer preview is in Chrome 29. Actually, it's in Canary as we speak, going to dev channel. I don't know what exactly the dates are, but within a few days, I hope. So there's a flag. You can go to About Flags, and you can look for Portable Native Client. You can toggle the flag. Toggle the flag, go to the Chrome Web Store, find our Portable Native Client examples, and you can try it out yourself. And here in a couple of minutes, I'll show you some of that running. You can see it for yourself. What we're really after, though, is this is an early preview. Things may be changing. We're looking for your feedback. What did you see for translation time? What did you see for the performance that we delivered for you? What did you see about the executable sizes, et cetera, that you might want to play with? We want you to give us feedback on what you observe at gonacl.com. And that's still a work in progress. We've put up some portable native client stuff that's just very, very much in the beginning, but we're going to be adding more as we go along. But the things we do already have, we do have an SDK for this. And it just so happens that it's already part of the native client SDK. If you've downloaded the more recent native client SDKs, say you pick the 29 SDK, you have the compiler, the debugger, the libraries that will build portable native client applications for you. And also the NaCl port stuff, which has recently become part of our SDK story. So you can see there's a bunch of libraries there that we have ported. And so you can build applications with a lot of these things as well. And you're probably asking yourself, so porting libraries, why did you have to port libraries? This is a compiler tool chain. Shouldn't I just be able to compile anything just by changing my CC variable in my makefile? Well, there's a little more to it than that because it's native code, it's running in the web browser. We need secure APIs for doing these plugins. So where your native application might have used message queues or event registration mechanisms that the operating system provides, now your application is going to be talking to the browser to get those kinds of event streams. Furthermore, where you might have gotten a hardware device context, an HWind or whatever, to scribble your 2D application's output into, now you're going to have to change those to use secure interfaces that actually interface with the browser. And last, and of course, unfiltered file access is not going to be okay, so you'll have to do some work to actually make file accesses work. And we have examples of this in our SDK that you can work from. To start with, we have a very vibrant developer discussion list, and you can join that. Or, last year, a couple of my good friends were here. That's Colt and Noel, and they gave a talk about porting a native client application in 60 minutes. So they took an application, took it from a running native application on Windows, used some of the tools that I'm showing down there at the bottom. They used the Visual Studio integration that we have. They used the debugger that we have, and they showed how to take it step by step through this long sequence of steps here, most of which is about just building things to be PPAPI compliant. And that's where you're going to spend most of your time as you port an application native client, is the PPAPI translation. And since we provide threads in these environments, particularly converting threads from one threading package to P threads can be a challenging part of that equation. So there will take some time in porting, but once you've got it ported, then you have a native client application. So what does it take to bring a portable native client application? Really one more step. That one more step is that you need to remove assembly code. As I said before, these are portable. They're not tied to a particular instruction set architecture, so having assembly code just violates portability on its very face. So you have to remove the assembly code. But that's pretty much the only thing that you have to add. You need to take another little step back and say, we're bringing native binaries to the web. We're bringing large, immersive, high-performance applications to the web. These may not be small, right? So one of the web design principles that you'll need to be aware of in doing this, now there are many versions of this sort of thing, but it has to do with the startup experience, right? That when you surf to that page, the user's sitting there waiting and waiting and waiting while you download an application. Be that a Naci, or a large JavaScript file, or a PXE, it is something that the user wants to be aware of something going on, wants to be aware of, and be able to deal with as part of the application experience. So when I surf to this SSH page, the translator is going to kick off for us. Now I said that we're going to stream translation, so the download time and the translation time are largely overlapped, but there will be a small addition to the download time to do the translation. So we provide you with progress events. And the progress events will be able to, will tell you in the JavaScript, I'm making progress. I've got this much of the code actually compiled, and you can put a progress bar at the top of your application. I'll show you that in a second here in an example. So that's one thing you can do. Another thing you can do is think about your application architecture a little bit. A lot of those examples I showed you a while ago of things that people have done, cool things that people have done with native client, were games. And games tend to have this property that you have maybe a medium to large application and a huge bunch of assets, right? You have a lot of 3D textures and game areas, et cetera, that you want to download. So if your application architecture says, I'm going to have the executable actually slurp down the assets, then in a system where you're pulling down a large executable, translating it, and then having to have it start running, before you start pulling any assets down, it's going to be a while before you actually get to useful work that the user can experience. Maybe if your application has a static asset list that you can know ahead of time, say it's got a few animals for your games that you want to put up, and you know those ahead of time, maybe a better way to do it is to have the JavaScript request those assets put them in a local HTML file system, and then let NativeClient open the local HTML file system afterwards. This gives you the ability that the assets are being downloaded while the translation's happening, and maybe even dovetailing with some of the download of the PXE itself, and gets you to useful work in the game or the application at large faster. Lastly, I told you I had that fiddle in there, that one extra entry in the manifest file, and that was to control what we called optimization level. I told you before that PXE to NaCl translation is actually the back end of a compiler. So there is some amount of optimization that still happens in that part of the compiler. Such things as register allocation and high performance scheduling can take some extra time and produce some extra performance. So we provide the developer with the ability to specify, I want low optimization, which gives you faster translation time and about 50% of native performance. Or you can request higher optimization levels, take a translation time slowdown, and get a much higher performance, 80+% of native code performance. So these are the things that the developer can do to try and improve the user experience. So let's get concrete about the translation rates. So since we're adding translation, which was something that was not there in NativeClient, we have to talk about that just a little bit. So as you can see on x86, we're doing about 750 kilobytes a second, which will about keep up with the average American's DSL sort of connection. I think the average American's bandwidth is about, 6 megabits a second or so nowadays. So we can keep up with that. So we think that it's reasonably balanced against that at the moment. ARM is a little earlier in the process, and we are seeing a lower number for ARM, partly because the processors aren't quite as beefy, but also because we know there are some features of the ARM translator that we haven't brought to bear that are going to speed ARM translation considerably. And then if you want optimized code, as I said, if you want more optimized code, 2 to 3 times sort of slowdowns, but with the considerably higher performance that you get for it as well. Performance. I already said, what is the performance number that you see? Well, we've done a few benchmarks. We're going to do a lot more. We're still in the process of gathering a lot of benchmarks. But the Box2D benchmarks at 0, we're seeing about 55% of native performance. And at 02, we're seeing 85%. For spec, about 50, and more like 90% of native performance. Spec is a kind of a standard platform CPU-intensive benchmark suite. So we think this is a pretty good start. We have a lot of additional optimization work that we're going to be doing and a lot of additional translation time performance changes that we're working on. It should be emphasized that the translation stuff that I just talked about a second ago, that's still single-threaded translation for us. So we haven't done multi-threaded translation yet either. So I talked about the developer. I talked about the user. So how does the user get the cool application that the developer built in PNaCl? Instead of putting it in the Chrome Web Store as we did with NaCl, it's going to be in the web. You put it up on your favorite Apache server or whatever your server of choice happens to be, it's going to be in the web. So let's talk a little bit about applications actually running in the web. So this is the PNaCl examples extension that I talked to you about before, and this is running one of the benchmarks or the examples that's there. This is to start our favorite spinning cube from the demo from last year, and you can see there's a little bit of a pause at the beginning. That's the translation time and the download from the local machine. That's the first time experience. And after the first time, it pulled it from the cache, it just starts. And even the startup time is improving because we're doing some NativeClient improvements actually that'll reduce the overhead of validation, which you can still occasionally see. So you can see it's not a terribly long pause to start with, but it gets even better on the second time. Here's a little bigger application. This is bullet physics, and you can see there's our progress meter going, and we're done. And there go our 500 cylinders falling. And here it is on the second time. You see the progress meter move so fast you couldn't even see it. And we're ready to go. Lastly, if you build without optimization, you can see the progress bar chugs a little faster and gets you visually pretty close looking performance. So that's the O-level translation that I talked about before. That versus, this was O0, the previous one I showed you, uncached, was O2. So hopefully you've seen there's some real potential here. We're really excited about this. We think this is going to bring us the ability to really put some cool stuff in the web, really immersive, high performance, native applications in the web. So we're working really hard now on bringing that out into the market. We're planning for a launch. We're working hard toward a launch. And we're going to bring all the instruction set architectures that you had with NativeClient with the first launch. We're going to have threads and atomics day one, as we've always had with NativeClient. And as I said before, we'll have the SDK full of all the tools that you've come to know and love. The Windows Visual Studio work is still sort of ongoing. That may be a little later, but for the most part, you'll have all the tools that you had with NativeClient, especially the debugger. This was one of the things that we're very proud that we have added recently to the NativeClient development suite. Unfortunately, we have to, for the first release, we've had to defeature SIMD instructions and C++ exception handling. These are the two things that we really wish we could have delivered in the first version, but I think we're probably not going to make. So we have a first update already sort of in the works, and the first update provides as one of its big benefits. We'll bring SIMD instructions. For a broad class of SIMD instructions, things like 4-wide 32-bit float additions and multiplications and places that sort of strike the sweet spot in these applications, we think we can do those in SIMD. So our first update will have that. And in the second update, we'll hopefully bring C++ exception handling and resolve that issue. A couple of things to mention are that dynamic linking support and JIT support are sort of longer term issues we're working on. We're very interested in getting those up and going because some of our games have used JITting especially. We have some ideas, but those are longer term. So on the user side, so the user experience, we're going to have translation caching from day one. We're going to have optimization level control so the user can say whether you want that splash screen to be compiled quickly and up in front of them or whether you want your physics engine to provide the utmost performance. And we're also going to give the progress events so that you can build UIs that tell the user what's going on. And as I said before, we don't have multi-core translation yet, but the guys in the team are all chomping at the bit to do this. So at some point in the not too distant future after that, we're going to have multi-core translation. So we also have some ideas for the O0 side for some really fast O0 code generation, and we're looking into that. And we're not quite certain when that would probably intercept, but that's also something that we're considering bringing fairly soon. So let's sum up. Native code. It's run securely in Chrome in the open web. 80+% of native performance, 85, 90 even some of those examples. You can try it right now in Chrome 29 Canary and hopefully dev channel within a few days. And we're shooting for Chrome 30 as our launch. Thanks. Questions? If you want to step up to the microphones for questions.
So I had a quick question. It may be, certainly. I'm not sure if it's a dumb question or not, but it seems as though you've built an abstraction layer that allows me to write native code and build it to LLVM, and then you can then translate the LLVM on the browser as you demonstrated, and the translated code is cached. So my question is, let's say if I build an application that's really successful and millions of people all over the world download it, millions of people all over the world are going to be compiling and translating this the same way. Why is this not done on the server side, or even why can't I do this as a developer and sort of do a cross compilation?
Okay, so that's an excellent question. So the question is why, so millions of people, you think of millions of watts. spent on translation, let's say. Yes, it's also yeah, it's millions of seconds of people's lives spent in this thing, perhaps. Yeah, it's an excellent question. So this is for so there are a variety of reasons. So doing the translation actually on the platform provides the ability to take advantage of the specific particular platform we're talking about. So I buy a latest generation Intel or AMD or ARM, whatever, and it happens to have some super microarchitectural feature. Translation there would allow the possibility of optimizing for that specific user's specific hardware. That's one thing we've always talked about. But no, in the broad, moving things up and say, in a place where I have, for instance, an install step, right, where I get it through an app store, then translation up in the cloud someplace obviously makes sense, or translation, caching it up there someplace. Even if you're surfing the web, maybe having a proxy that can do some translation, this makes sense. These are things that we'd like to investigate further, and definitely the technology base we've built lends itself to doing things there. It's more of a question of deployment and user model that is the issue at the moment.
Sure, but I mean, so if you look at things that are deployed today, like
Yeah.
games or whatever, right?
Mm-hmm.
So sure, there are millions of different permutations of hardware architecture, but today this isn't done this way. Right?
No, exactly.
Native applications today,
Yeah.
when I distribute are not done this way, right?
Right. Well, I should say also, the SSH application that I showed there actually right now is in the Chrome Web Store. It was built using the PNaCl toolchain, but they force translation ahead of time and install it in the Chrome Web Store. So that's an option for you also. And so this sort of thing is something we're considering. It's really a sort of a user model sort of question that we're trying to resolve. I think it's a great idea to do what you're saying, but there are questions about where do you host this caching mechanism? Where do you get these things from? Definitely, excellent question. Over here?
Yeah. I had a question, like Dart recently added support for SIMD instructions.
Yes.
So how you see Dart and PNaCl in the future?
Well, I think that the two are complementary technologies to start with. I think that we're really after taking the C++ application. I've used C++ as a sort of a broad umbrella for all kinds of native applications that might exist out there. Where Dart is much more targeted at sort of the web applications, viewed more in that sort of category. But if you're asking the question around the performance, Dart is still a language that supports a richer and more dynamically typed sort of execution model than we're targeting with this. So we believe there's still a performance gap between the way their code runs and the way native code, which has been, for instance, fully devirtualized and targeted toward a specific set of polymorphism. So I think we think there's a performance gap that we move toward sort of the higher end of, as opposed to Dart or JavaScript today. The SIMD instruction thing is sort of, we're going to get SIMD instructions, and they having SIMD instructions, of course, moves them closer to us, but there's still a performance gap there, I believe. So, cool. Yeah. Over here to the left.
Yeah, so having developed at the native layer for Android, I can really appreciate this. So you mentioned there's going to be no support for assembly. Are you going to provide some kind of hint so that we can, for example, kind of hint for provide some cues for the SIMD compiler? We've seen tremendous use of the ARM7 Neon.
The SIMD instruction stuff in particular. So the likeliest thing is a set of intrinsics. So we're going to have a set of intrinsic functions that you call, say, I want to do a 4-wide multiply or 4-wide add or whatever, and you'll use some data types. LLVM has some of this stuff for Intel in particular, or for Neon in particular, but there's no sort of common way to express it. Now, for the specific things, say I want to do a horizontal summation, which only some platforms support, or I want to do some sort of transcendental or something that maybe somebody's vector instructions support. That kind of discussion we've had a few times internally. Maybe we'd like to provide some way to key CPU ID and to say, I'd like this version to run with this class of CPU, and then have maybe some platform-specific intrinsics. But that's a very early discussion, and we haven't really gotten very far with that. We fully recognize, for instance, there are instructions to do AES encoding better on some Intel and AMD parts. We'd like to be able to get to those things. And it's really hard to do that with a portable intrinsic today, but yes.
Yep. Thanks.
Thanks. We're good?
Yes, you're using LLVM for this.
Yes.
But up to now, the intermediate language in LLVM, that was an intermediate step in their tool chain,
Yes.
which means that they can upgrade it, add to it.
Yes.
And you are making it a persistent thing in a file
Yes.
all over the world on servers.
Yep. That's another excellent question. So
How is that going to work?
how are we going to make it persistent when it's really a compiler intermediate representation? So there was a nice discussion on the LLVM mailing list, I don't know, a year and a half ago or so, where it was exactly that statement. LLVM is a compiler IR. So we have been working very hard recently on simplifying. I kind of obliquely said this earlier, simplifying LLVM IR. So there are some complicated things, complicated instruction patterns that seem to raise the risk of changes happening. Attributes on functions, attributes on variables, which have just gone through major morphs. These are things that we're severely restricting those down to just a small set that we believe we can support. We've also cut the readers and writers of LLVM IR off. We're going to keep frozen versions of those that will allow us to translate into the more recent versions that we use for the back end. So the physical writing of it will always be in the format that we sort of control. And with the simplifications that get rid of linearizing addressing and some of the other things that are, we think, potentially vulnerable to IR changes, we've tried to write those out. We have a series of passes that simplify those away and hopefully reduce the surface of LLVM IR susceptible to change.
So what you're saying is that you are freezing the intermediate language, or are you?
Well, we have a versioning scheme, so we can turn the version when it really diverges too severely from that. But we think that we've reduced the likelihood of it diverging very severely by these simplifications.
Okay, thank you.
Thanks. Over here.
Two questions. One is regarding benchmark. You saw the performance numbers, but are the numbers similar on ARM? And the second is, once Google Chrome 30 is being released, would you support PNaCl on any website?
Okay, so with regard to the ARM question, I don't have the ARM numbers with me at the moment. So traditionally when we run the ARM numbers, again, we see numbers that look like the x86-64 sort of numbers. So it'd be toward the 80% as opposed to 90% sort of range for the high end of these things. So I would guess it would be there, but I can get those numbers and ask this on NativeClient Discussed, and we'll be glad to publish those things out there as well. Now, the other question that you just asked was about, will it be available in the open web, I believe, right?
Yep.
So the intent is that actually, yes, it will be available in the open web. You can host a site that has a manifest file that refers to a PXE, and you point Chrome at that. You won't need to have any sort of install step or any sort of flags or any sort of web store to get it enabled.
Thank you.
You're welcome. Do I have more time? Okay, looks like we're out of time, folks. I'll be over in the chat area for the next 15 minutes or so feel free to come by and we can talk some more.